Hello, let's talk about the dynamic programming, a common technique used for algorithmic problems. So it's a technique for computing the answer to a problem from answers to the same problem of a smaller size. And we can compute the answers to some very small size in a trivial manner and then just use some formula to compute it for like bigger values. It has some overlaps with recursion because recursion also like deals with like using function to call itself. The formula is typically established by looking at what was the last step or action to reach the current state. Suppose for like Fibonacci numbers, suppose we have like fi equals to fi minus 1 plus fi minus 2. So I'm gonna go through like another next problem in example which like shows this concept a bit more. It's typically computed using for loops, but also we can calculate it using recursion with memorization. And another trick is like you can also reduce space complexity by only storing a part of most recent values needed for computation, not all previous values. So for example, for like Fibonacci sequence, you only need like to store 3 variables. You can keep like shifting values in them instead of storing a full array. It's like a minor technique because usually like time complexity is the main concern, but still a nice thing to know. Let's take a look at jumps. A person can jump from a position I to positions I plus 1, I plus 2, and I plus 3. Find how many different ways are there to jump from the position 0 to the position n, a modulo some number. Let's define fi as the number of ways to jump from position 0 to the position I. Then f0 is 1, f1 is 1 because we just do one jump, and f2 is 2 because we can do like one medium jump or like 2 small jumps. For bigger I, now let's look at the last jump that brought us to the position I. It can be of lengths 1, 2, or 3, and all of this leads to like a unique jumping sequence. So in the first case, it was from position I minus 1, so we get fi minus 1 ways to reach that, and so etc. So overall, we get fi is fi minus 1 plus fi minus 2 plus fi minus 3. Also, don't forget to take modulo so you don't have to deal with like large numbers. Note that we can also compute this in a linear time by using for loop, but also there is like log n algorithm with fast matrix multiplication, but that's out of scope for now. Let's take a look at the cheapest path to the corner. You're given an array n times m with positive integers, indicating the cost to enter each cell. A00 is 0, so starting cell, and then we need to reach position n minus 1, m minus 1, while moving only by increasing one of your coordinates. And find the cheapest path. Strictly speaking, integers also don't have to be positive because of limitations from the movement. It would work with negative as well. So let's define Fij as the cheapest path to reach Ij. Then we have some edge cases, like f00 is 0, and fin minus 1 and minus 1 is the answer. For I is 0, we only can reach it from like 0j from 0j minus 1. So we have f0j is f0j minus 1 plus a0j. And similarly, fi0 is fi minus 1, 0 plus ai0. For other cases, there are 2 ways to reach ij, given as fij is like minimum from like those 2 ways, fi minus 1j, fij minus 1 plus aij. So, and then let's take a look at balanced bracket subsequences. So sequences of open and closed parentheses of the same type is balanced if it's either empty or can be constructed as open bracket A closed bracket or AB, where A and B are balanced sequences. You are given a sequence S with these brackets. Find how many balanced subsequences it has, not necessarily contiguous and without the duplication and modulo some number. For example, for S is like closed open open, the answer is 1, just empty subsequence. And for S equals to like open open close close, the answer is 6. So here we take a technique where we expand the scope and compute actually a bit more than what's required of us, but then we can get nice formulas for that. So let's expand the scope by defining Fij as a number of subsequences from 0 to I to have j unbalanced open parentheses and all balanced close parentheses. F00 is 1. Like we basically like have to not take the first like 0th character. And F01 is 1 if S0 equals to open, else 0. And it's like 0 for like j more than equal to 2. So if Si is closed parenthesis, then if we take it, then we need to have parenthesis balance like j plus 1. So Fij is like Fi minus 1 j plus 1, or we don't take it, then we just reduce problem to like same like balance, but then like smaller size, so Fi minus 1 j. If Si is equals to open parenthesis, then the only way to achieve zero balance is not take it into our consideration of our subsequence, and it's like Fi0 is equals to Fi minus 1, 0. And then for j more equals than 1, we just can like take it. So the balance has to be like lower for the previous subsequence of F minus 1, j minus 1, or if you don't take it, it's like Fi minus 1, j. And finally, the answer is Fn minus 1, 0. Cool, let's get to homework. So I encourage you to try to solve it yourself, and then I will do analysis after some pause. So first problem is compute how many balanced single type bracket sequences are there of length 2 times n. For example, if n equals to 2 is like 2. Another problem, given two sequences of numbers, find the longest common subsequence, not necessarily consecutive. For example, for this 3, 2, 5, 4, 7 and 4, 2, 4, 6, 7, the answer is 2, 4, 7. In another problem, we have a knapsack that can hold weight up to W and goods of weights Wi and values Ai. Find the maximum value of goods that can be fit into a knapsack, and each goods quantity is unlimited. Then like let's consider W is like relatively small. Okay, let's do analysis. So first one, we'll do dynamic programming. Fi is like number of balanced bracket sequences of length 2 times I. So F0 is 1. And then basically for every sequence, first bracket would be open. So there would be somewhere like a matching closed bracket. So and then this closed bracket can be like on even positions. So let's do iteration where this like matching closed bracket is, and then like between those pairs of like matched parentheses there would be a balanced parenthesis, and outside of it there also would be a balanced parenthesis. So we have like a sum of like multiplications, something like Fj like times Fi minus j minus 1 for j starting from 0. And then yeah, this gives us like a full answer later. So for subsequence, we're gonna define like a dynamic programming. So Fij is what's the answer like for the longest length for like subsequences up to I and up to j, from 0 to I for the first sequence and from 0 to j for the second sequence. And then we define some like additional array Bij is like what was the like number we took for the sequence to like reach that, or what the action we took. So then we can reconstruct the answer later and don't have to like store full answer into like every cell. So then basically like if AI equals to Bj, then like we can take that. So it's gonna be Fi minus 1 j minus 1 plus 1. And then we can also like either skip like i's element in A or skips j's element in B. So it's gonna be Fi minus 1 j and Fi j minus 1. You can show that actually if we can take the element here, it's always beneficial to take it. But for simplicity, we can just like take just maximum of all the values available. And also don't forget about edge cases. For the knapsack, there are multiple variations of this problem. It's kind of classical problem. So for this variation, we define Fij for like what the maximum value we can get by using first I, like products from like 0 to I, and achieving weight, total weight j. Then we just compute this, we compute like initial cases, so something like f00 is 0. Basically fi0 is like 0. As we get no value, cannot put anything. And then for a given weight, we determine how many of each ith good we pick. So it's gonna be, suppose we pick like k. So then we reduce a problem to weight j minus k times wi, and we add value k times ai. So this gives us a formula of like a value to consider. And then we just iterate of like how many items of I we get, and get like a maximum of the results. That's gonna be it for me for now. Thanks for watching. Let me know if you have any questions.